Hey everybody, this is AB Calc section 6.2, day number 1. We're going to talk about area between curves. Your goal for today is to be able to use integrals to find the area between two curves. Okay, so class opener, what is an integral and how is it connected to area? Well, an integral takes on the notation integral from a to b of f of x, f of x dx. And that's equal to, using the first part of the fundamental theorem, f of b minus big F of a, given that the derivative of big F is equal to f of x, right? And geometrically, that just means the area, right? The area between f of x and the x-axis, which is actually the function y equals 0, right? That's the x-axis. So what we're going to be doing in this lesson today is we're actually going to be talking about the area between functions. So you've already been doing this without even knowing it. So if we look at example 1, it says this is apparently a review example, which is true, and the graph of f of x is equal to x squared plus 1. Find the area between under the curve from x equals -1 to x equals 2. So geometrically, we can clearly see that that area is going to be enclosed here. Now, in this case, we have an upper function, right? This upper function on this interval is x squared plus 1, and our lower function in this interval is actually y equals 0. So I've got y equals x squared plus 1. I've got y equals 0. And thus I can find this area, I'll highlight it here in yellow, which would be represented by the integral from -1 to 2 of our upper function minus our lower function. Now, up to this point, we didn't really consider that there was a second function, right? This second function here, because, well, we just thought of it as the area trapped beneath the function and between that and the x-axis on whatever interval. Okay, so you can work this example out on the side. The work for this is pretty basic, but I want to introduce to you this idea that when you have two functions, let's call this f of x, and let's call this, let's go purple. Let's call this g of x. If I want the area between the two functions, right, trapped in between them, let's assume we can trust the end behavior, right, and that's the only area trapped between the two, right, because if g of x continues on and f of x never catches to intersect it, then, and the same in the direction as x goes to -infinity, then this would be the only area trapped between the two curves. So you have to be careful about that. But what we'd have to do is we'd have to find these points of intersection. Let's call this x1. Let's call this x2. So the area between the two curves would be the integral from x1 to x2 of the upper function minus the lower function. So that'll be f of x minus g of x. Okay, and that would be the setup, at least without obviously working through the work, since this is a general case, for finding that area. Now, interestingly enough, right, is it possible that two functions, right, could intersect multiple times? Well, absolutely. So, for example, let's take these functions. Let's go sine x, and so this would be x equals pi. This is x equals 2 pi. Call that y equals sine x. And let's go cosine x, which will look kind of like this, from 0 to 2 pi. And say we asked you, right, for the area trapped beneath the curves, or between the curves, excuse me, from 0 to 2 pi. Okay, so that would be That would be all of this. Now we don't want net area. Anytime they ask you for the area between the curves, we're considering positive area. We're considering every area positive. So we want to accumulate this area, let's call it A, this area, let's call it B, and this area, let's call it C. Okay, so if I were to go about this in a traditional sense, right, I wouldn't want to write this out, right? I wouldn't want to go 0 to 2 pi of, let's say, cosine x minus sine x. Right, and the reason for that is because on this middle interval that accumulates area B, sine x is the upper function, right? So that presents a problem. So one of the solutions to that problem is to take the absolute value of the difference. Okay, the other solution to that problem is to find the points of intersection, right? And if you got a calculator available, this is your option. This is what you should do. If you have a calculator available to you, you go that route. You use the absolute value of the function or the difference of the functions. It doesn't matter which one is first, whether you put cosine first and sine second or the other way around. That is what you would do with a calculator. Use the power of the calculator. If you don't have a calculator, okay, so if it's a no calc, okay, what you want to do is you want to split this up. Right, I would split it up, and it looks like this would be pi over 4, and this would be, I think, 3 pi over 4. So you're going to want to work with 3 integrals, 0 to pi over 4 of, and I'm just, for the sake of brevity, I'm gonna put f cosine as f of x, and sine as g of x. Okay, and you can work it out in a couple of different ways. Okay, one of them would be anywhere that the cosine is the upper function, you just take f of x and you subtract g of x. Okay, so I would do that for intervals from 0 to pi over 4, as well as the interval from 3 pi over 4 to, oops, I'm sorry, that's not 3 pi over 4. That should be, oh gosh, is that 5 pi over 4? Yeah, that should be 5 pi over 4. That was my mistake. This should be a 5. Okay. Plus, now you could, in the second interval, do this a couple different ways. Go from pi over 4 to 5 pi over 4. And you could take and flip the 2. Right? So you could take g of x minus f of x. Right? That would negate the sine. Okay, that's also an option. And then in the third, right, in the third integral, again, I just go back to what I did with the first integral expression, which is go from 5 pi over 4 to 2 pi of f minus g. Right, I'm starting to get a little bit lazy with my notation here, so don't do that. I'm trying not to, but it's just a lot of writing. Okay, so I want to talk real quick about this interval, right? Right, let's say you kept f as the first function. Okay, clearly that area would come out to be negative. And what you'd want to do then is after you find that area, right, whatever that ends up coming out to be, okay, you take the absolute value of that area, right? So then each of the areas would have a positive magnitude, and you could add it up and get that total area. But if you're ever asked for area, you should assume total area. If you're ever asked for area between two curves, assume total area. The only time you should ever work with net area is if you're explicitly asked for net area. So let's look at a few examples. I might have gone a little too far with that, but that's okay. So let's continue on to the next example. All right, so pretty basic here in example 2. It says find the area or the region between f of x, which is x squared or x minus 1 squared, and g of x, which is sine of x plus 3. Okay, so clearly the weirder of the two functions we can identify as g of x, and this quadratic we can write as f of x. Okay, so on this interval, what we need to do is we need to find these values, right? Okay, so I got to find the points of intersection of those two. Now, if I were to in order to do that, I'd set f of x equal to g of x. Well, this equal to sine x plus 3. That's going to be really hard to do algebraically. So what you're going to do is use your calculator. And when we find the solution, right, so I'd type this in for y1, type this in for y2. Actually, I might flip that just because I'll show you in just a second here. So I'm gonna type g of x in for y1, and the reason is because, well, I typically end up taking y1 minus y2. I'm inclined to do so. So I typically put my upper function as y1 just so I don't screw it up. And then I'm going to put this in as y2. And I'm going to solve. So I'll come back in just a moment with those values. Okay, so just a few things as you're working through this. As you're finding these points of intersection, you want to make sure you've got a nice window where you can see the points of intersection. So I think in my window I went x min of -2 x max of, I think I said 5, and then I went y min of 0 and y max of 10, I think it was, right? And I could see this portion of the graph clearly. Okay, so now what you want to do is you want to find the points of intersection. So press second trace, second, and then trace, and then go to the intersect option. Okay, and what I want to do is find the 2 points. So I'm gonna call this point B, and I'm gonna call this point A. So my calculator, that was weird. My calculator yielded for me a B value, and you never want to round this in the intermediate step, but my calculator gave me a B value. I'm just gonna write it here, knowing that I'm going to store it, not use this rounded value, but I get 2.821 out to 3 decimals. Okay, so I'm going to store this. So I'm going to go back to my home screen and press enter. Oops. What's going on? My calculator's getting weird on me. Nope. Why is that doing that? Okay, hang tight. Okay, so when I get to my home screen, I'm going to press second and the negative symbol, right? Above the negative symbol, you'll see ANS. Okay, that's going to pull this number up right here with all the rest of whatever's after it. Then I want to do this. I want to press stow. So then that should come up, and then you press stow. And I'm going to store it as B. So I press alpha, and then I press apps. You can see right above the apps is like this B. Okay, alpha apps, and then press enter again. So this number is now stored as B. Okay, let's do the same thing for A. Okay, for A, I get something like negative 0.5688616002. So I've stored A as 0.56, oops, it's negative, sorry, 886160002. Okay, so now I do want to make one specific point. If you are going to write this down on your paper and not just store it and have your calculator remember it, you need to write it down out past 3 decimal places like I just did. Okay, so now we come to the execution step. Okay, if I want to find the area between these two, let's put it in blue, right? This area right here is going to be the integral from A to B, and I'm allowed to write that as long as I have defined those values, right, and not rounded them, of g of x minus f of x. And you are allowed, you don't have to be specific, right, about what those functions are, because we've defined them, right? They're defined here. We've already linked them. So I'm allowed to just write this notation. So I use math 9, and I'm going to go from alpha math, which will give me A, from alpha apps, which will give me B, of alpha trace y1, right? Make sure you got y1 as your upper function, minus alpha trace y2. Okay, so in my calculator, I see this, a to b of y1 minus y2 dx. Okay, make sure you got your dx in there. And boom, I get an area between the two of 8.661. Now, if you were to, let's say, terminate these, that's poorly drawn, but let's say you went to 3 decimal places and just used those values. Well, your answer potentially here, if you rounded an intermediate step, may come out to be something slightly different than what it actually is. Okay, let's continue on to example 3, very similar. Let's go upper function, lower function. So I'm going to say that x plus 4 is the upper function here. Okay, so I'm going to call that y1, x plus 4. And then y2, of course, is this quadratic. So y2 is x squared minus 2. I think this is reasonable to do without a calculator. So let's find where the 2 are equal. Let's find out where x plus 4 is equal to x squared minus 2. Well, that would be where 0 equals x squared minus x minus 6. Let's see if I did that right. Yes, I did. Okay, now I'm going to factor. So that'll be x minus a 3 and x minus a 2. You might be able to guess graphically. You can see negative 2, negative 2 and a positive 3, right? X equals a positive 3. That would be where the points of intersection are. So at x equals negative 2 and at x equals a positive 3, y1 is equal to y2. Now, I can clearly tell from the graph that these two will never intersect again. A line will never catch up to that part of the quadratic in either direction. So I'm going to mathematically work this out. I'm going to take the integral from negative 2. Analytically, let's work this out. And we're going to take our upper function, which is x plus 4, minus our lower function, and I'll get down to the nitty-gritty here in just a second, x squared minus 2. I just want to get the setup nicely set there. Okay, now, the biggest mistake of any calc student that I've seen at this point is you've done the hard work. Now you just have to make sure the algebra is good. So this would be negative x squared. Okay, and then we get plus x, and then we get plus 6. Okay, dx. All right, so we're going to integrate this. All right, so let's integrate. That'll give us negative x cubed over 3 plus x squared over 2 plus 6x. And that's going to be evaluated from negative 2 to 3 using the first of the fundamental theorems. Okay, so I guess I got to do some math and try not to screw this up. This is going to be negative 9, okay, plus 9 halves plus 18. So that would be big F at 3. Our antiderivative evaluated at 3. Let's make sure that would be negative 27 over 3, which is negative 9. 9, which is 3 squared, over 2, which is good. And then 3 times 6, which is 18. Good. Okay. Minus our antiderivative evaluated at negative 2, which would be a positive 8 thirds. Plus 4 over 2, which is 2, and minus 12. All right. This is the part where things start to go awry because our fractional skills are not as good. Okay. So negative 9 and 18 is 9. So 9 plus 9 halves is the same as 18 halves plus 9 halves. That's 27 halves. Okay, I'm going to take away, well, that's going to be 8 thirds minus 10. Well, 10 is really 30 thirds. It's going to be negative 22 thirds. Negative 22 thirds. Okay, so now I got to combine these. Oh goodness, is that 81 sixths minus a negative will just be plus 44 sixths. That comes out to be 125 over 6. And I think that's good. provided you're not, in a testing environment, you can always go back and check and see if your answer comes out to be equivalent to what it is you got analytically. And the algebra was right on. All right, let's continue to one more example. All right, here we go, example 4. A little bit different here, but let's do it. Find the area between y equals the square root of x. Okay, I'm going to call this y1. Here's square root of x. And y equals negative 1/2 x squared plus 4. It's going to be a red curve. And the x-axis, so we got to throw in the x-axis here. So I'm going to call this y2, and I'm going to call this y3. Well, y3 just equals 0. So very interesting here. A couple ways to do this, but I'm going to try to keep it simple for this video. What I'm going to do is I'm going to find this point of intersection. Okay, I'm going to find this point of intersection, and I'm going to find this point of intersection. Okay, how am I going to do that? Well, first of all, we know this point of intersection is point 0, 0. This point of intersection is where y1 is equal to y2. So we'll work out that algebra in a moment. And this point of intersection right here is going to be where y2 is equal to y3, right? Or where y2 equals 0. All right, so the next thing I'm going to do is I'm going to go ahead and enter y1, y2 into my calculator. I'm not going to enter y3 because, well, the calculator defaults to finding the area under a curve trapped above the independent axis. So for y1 and y2, I'm going to plug those functions in. So y1 was the square root of x. Okay. y2 is negative 0.5 x squared plus 4. Okay, now when we think of upper function, lower function, I'm not going to think of anything other than each of the functions individually. So I'm going to find this area here in green by taking the integral of y1 with respect to x from 0 to what I'm going to call point A. Right? I'm going to call this point the point of intersection at x equals A. I got to find that in just a moment. And then I'm going to add, let me make this green to keep everybody happy. And then I'm going to add the area that I find here. So this would be the area from A to B. Okay, and this will of course be point B, where we find the point where y2 equals 0, and of course we're going to integrate then y2 with the calculator with respect to x as well, and that should equal the area that we have in sum in total. Okay, so let's find points A and B. Okay, so my value for A came out to equal 2.237, 876, 893. Okay, and my value for B came out to be 2.82, 8427, 125. Okay. So I'm going to then use my ability with Math 9 and the definite integral in order to find this area. Okay, so using that, and of course now one thing that's important to note is that here I was able to do second trace intersection, but here I had to do second trace 0. Since I didn't punch this in as an actual function, I had to do a left bound and a right bound and then enter again, and that gave me this value x equals b. Okay, so I'm going to go ahead and go off screen and come back with an answer. Alright, so my TI machine comes out with 2.69 1, or 2.6907. Alright guys, that's area between curves. We're going to get into some more complex situations with that in day number 2. I did go a little heavy on page number 1 talking about area between curves, which may or may not have been necessary, but it'll at least give you a good heads up for day number 2. Alright, we'll see you in the next video.